Hello students, in today's class we'll be solving the example number 1. This example is based on the concept of drift velocity. Okay, drift velocity. We'll read the question, we'll understand the question, and then we will go for the solution. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area of 1.0 into 10 to the power minus 7 meter square, carrying a current of 5 amperes, 1.5 amperes. Assume that each copper atom contributes roughly to one conduction electron. The density of copper is 9 into 10 to the power 3 kg per meter cube, and its atomic mass is 63.5 unified units. See, we have to find out the average drift speed. Average drift speed, VD. Okay, this is unknown to us. What all things they have given in the question, information provided in the question is cross-sectional area, which is very small, 1 into 10 to the power minus 7 meter square. Then they have given us the current flowing through this cross section, that is 1.5 amperes. Then we have the density of our copper, mu of the copper, that is 9 into 10 to the power 3 kg meter cube, and its atomic mass, or A, equals to 63.5 U, and here U is the unified mass. There is one more statement given. See this. Copper atom. From here, copper atom contributes roughly one conduction electron. So whatever amount of atoms are there inside this cross-sectional area, in this cross-sectional area, whatever number of copper atom are there, that many number of electrons will be provided roughly, okay? Not exactly they are saying, maybe one provides 2 conduction electron, maybe one doesn't provide any conduction electron. So overall, roughly we can say amount of, or the number of copper atom present equals to number of copper atom present equals to number of conduction electron. Okay, so density says how many number of atoms are present in the particular copper atom. Density is what? Density here is mass per meter cube, that is in a particular given volume how much is the copper present. This is our density. When it is divided with unified mass, it will give us the number of atom present in that particular volume, and that many will be the number of electrons circulating in that cross-sectional area. Okay, that's why the density is important over here. And I'm taking rho as the density. Rho is resistivity also, but here the rho denotes the density. Now we will simply decode the B part of our question. In A, we need to find average drift speed. These all are the information provided. Now we will decode the part B. Compare the drift speed obtained above. Whatever drift speed we are getting from the one, we have to compare that. Comparing VD with thermal speed of copper atoms at ordinary temperatures. At ordinary temperature is room temperature. that is 27 degrees centigrade, which is equals to 300 Kelvin. Okay, and then speed of propagation of electric field along the conductor, which causes the drift motion. Okay, uh, at what speed the electric field is propagating, we have to compare it with that. Vd compared, this is B second subpart, Vd compared with propagation of electric field speed. Okay, these are the two subparts of this question. Now it's time for us to move a step ahead and learn how we can solve this. So, solution over here for part A starts. The direction of drift velocity of conduction electron is opposite to the electric field. If electrons are flowing in this direction, electric field will be in this direction. That is what we have read so far in our lectures also. That is, electrons drift in direction of increasing potential. Electrons drift in direction of increasing potential. The drift speed Vd is given by Vd equals to I upon NEA, where I is the current flowing, N is number of electrons, conduction electron, E is charge on that particular electron, and A is the cross-sectional area. Here for I we have 1.5 ampere given in the question. Cross-sectional area is 1 into 10 to the power minus 7 meter square, again given in the question. Given this is universal, that charge on an electron is 1.6 into 10 to the power minus 19 coulomb. That is the charge on an electron. The density of conduction electron N is equals to the number of atom per cubic meter, assuming one conduction electron per Cu atom, as is reasonable from its valence electron count of 1. This is even given in the question. They have said to assume that this is happening, and by Cu copper's atomic or the electronic configuration, we can find the same. Copper can give us 1 electron per atom. Then the cubic meter of copper has a mass of 9 into 10 to the power 3 kg. See, the density given was 9 into 10 to the power 3 kg per meter cube. So in 1 meter cube, how much weight of copper is present? That is 9 into 10 to the power 3 kgs. Okay. Since 6 into 10 to the power 23 copper atoms have a mass of 63.5 gram. See, 1 mole of Cu have atoms equals to Avogadro's number. Avogadro number. Okay. Now, in this 1 mole, what is the weight of the copper? 1 mole of copper have weight equals to its unified mass, that is 63.5. So we can compare these two quantities. They will be equal. Okay. So we have Avogadro's number of Avogadro's number, atom equals to Avogadro's number will be equals to 63.5 gram. So in 1 gram, how much will be the number of atoms? That is N. In that question we have seen I upon NEA. We got the value of I and A from the question. E is universal and value of N is something we need to find. Number of conduction electron. N is number of conduction electron. So that is Avogadro number divided by the atomic mass into the density. How much weight is there? So after solving this, we will get this many number are present in 1 meter cube. In 1 meter cube, number of atoms are 8.5 into 10 to the power 28. Now we will substitute this in the formula of Vd, that is drift velocity. Current upon current, this is current 1.5 divided by number of atoms into charge on each atom into this, that is our cross-sectional area. Upon solving this, we will find that drift velocity comes around 1.1 into 10 to the power minus 3 meter per second. M is here meter per second. Okay, meter per second. Now this meter per second is converted into millimeter. We have reduced this power. So it is 1.1 millimeter per second, which is very much small. Now we will go with the second step. In the second step, we were asked to compare Vd. Okay, we were asked to compare Vd with two things. One was the thermal copper atom, that is copper atom at room temperature. Okay, and the another one was with the propagating speed of electric field. Propagating speed of electric field. Now first of all, we will see the first case, the thermal copper atom at room temperature. At a temperature of T, the thermal speed of copper atom of mass m is obtained from half mv square, which is equals to 3/2 kBt, where m is the mass of the copper atom, v square is the speed at which it is moving, kb is the Boltzmann's constant, and T is the temperature at which we are describing all these things, and is thus typically of the order of kBt upon m. Okay, where kb is the Boltzmann constant. For copper at 300 Kelvin, this is the room temperature, okay. This is about 2 into 10 to the power 2 meter second. This figure indicates the random vibrational speed of copper atom in a conductor. Randomly at room temperature, this is the speed of vibration of the copper atom. Okay, this is our copper matter, and these atoms vibrate at a speed of 2 into 10 to the power 2 meter per second. Note that the drift speed of electron is much smaller, that is about 10 to the power 5 times the typical thermal speed of ordinary temperatures. This speed is very much lesser. Okay, see, I'll explain it. Vd is 1.1 into 10 to the power minus 3 meter per second, whereas our V of copper is at room temperature 2 into 10 to the power 2 meter per second. See the difference, it is 200 meter per second, whereas this is 1.1 into 10 to the power minus 3. See the power difference. If I'll write this in the millimeter, it will be 0. It will come around 1, 2, 3, 4, 5. 5 times 0 if we want to compare it with this, so that into 10 to the power 3 can come. Okay, so this is greater. Vd is smaller than V of copper by a factor of 10 to the power 5. Okay, by a factor of 10 to the power 5. So in general, it have a higher speed than this drift velocity of the conduction electron inside the copper. So the drift will be slow at room temperature, like at any temperature drift will be slow. Now the second, propagating speed of our electric field. An electric field traveling along the conductor has a speed of an electromagnetic wave. namely equals to 3 into 10 to the power 8 meter per second. Drift speed is in comparison extremely small, smaller by a factor of 10 to the power 11. See, normally all these electromagnetic waves travel at a speed of velocity, okay? Sorry, speed of light. Speed of EM waves equals to speed of light. Now, how can we say that EM waves travel at a speed of light? Because light is also a EM wave, okay? When we go with gamma, then we go with X-rays, then we go with UV rays, then we go with visible, so on, infra, micro and radio waves, okay? All these EM spectra is consisting of these EM waves, and these EM waves constitute light also as their part. So the speed of EM waves are always equal to the speed of light, that is 3 into 10 to the power 8. And here our drift velocity is 1.1 into 10 to the power minus 3, and our speed of EM wave is 3 into 10 to the power 8. See the difference between them. It is 10 to the power 11. A huge difference is there. Electric fields are traveling more and more faster than the drift velocity of these conducting electrons. So that's the question. We have provided the solution here. Hope you people got it. You understood it. Just go through the concept of drift velocity. It is easy. Only thing is you need to understand and you need to remember few constant values like Avogadro number, the charge on an electron, speed of EM wave, speed of light, and the formula like 3 upon 2 kBT, that is the thing which we have learnt earlier in our 11th standard already. Okay, so that's all for today's class. We'll meet up in the next class with a new topic. Till the time, have a good day. Keep practicing, keep growing.